Let's talk about chapter 4.4, which is called Differentials. Good first question is, why should we care? So it's a preview of parts of chapter 5 and 6. It'll be a little technique we use in chapter 6 especially, doing U substitutions. They're useful for doing little approximations based on a little formula, and differentials are also useful in error propagation. If you're in a chemistry lab or physics lab or something and you measure something to within a certain precision, and then you plug it through some physics or chemistry or biology kind of formula, and then you get an answer, you want to know how much precision is there in that answer. So differentials is a method that can tell you that. Let's think back to one of our big ideas of calculus. If you zoom in enough, most of the functions that we use in science and engineering and stuff tend to look, what do they look like? Hopefully you think linear. That's the big function. That's the big idea, right? So let's talk about our favorite formula for tangent line, or what else have we been calling it? Best local linear approximation. And another name we can give it is a linearization of a function. So try to remember what the tangent line formula or the best local linear approximation formula is. Ready? L of x, I'm going to leave a big gap there, f of c plus f prime at c times x minus c. Hopefully you remember that. If not, pause the video and quiz yourself. Try to write it down without looking at it. By the power of algebra, I'm going to move this f of c over to the other side. I'm going to subtract it from both sides. So then we have L of x minus f of c equals, and then I'll leave a gap there, f prime of c times x minus c. And then let's think about what each of these things is. Which one would you say is the old exact y value? Which one is the new approximate y value? Take a sec to think about that. Well, f of c is the y value at c. It is exact. So that we could say this is the exact old y value. L of x is a y value, and it's exactly on the tangent line, but there's a good chance it's not on the original function. So I would call it an approximate value for the y value at that new x value. So I'd say this is the approximate new y value. And then what can we say about the difference? That difference, that's the approximate change in y, right? If both of these were exact, then that would be the exact change in y. But if one's approximate, then the whole thing's approximate. So this is the approximate change in y. So should we call it delta y? Well, delta we usually use for exact changes. So we're going to call it dy, not delta y. Delta y we'll use for exact change, dy we'll use for approximate change. Then let's look over here. This x minus c, c is kind of the old x, x is the new value, c is exact, x is exact. I can plug in any value I want for x. And so these are both exact. So this difference, I can call that delta x. That's the exact change in x. If someone asks me for the approximate change in x, well, it's easy enough to compute the exact change in x. So we can also call it dx. That would be the approximate change in x. It's just an extremely good approximation because it's exact. So we can also call this dx. Okay, so we've got delta x, which is the same thing as dx. We've got delta y, which is not the same thing as dy. So let's make a drawing of what's going on. We'll have our x and y axes. Let's have c here, and x here, and we'll draw a nice curved function. So that's our original f of x. I'm drawing it in blue. And then here at C, I'm going to draw a tangent line. So let's label here C of, we did C and x. Let's label delta x, delta y, dx, dy, all that stuff. So based on these definitions, try to show what is dx, dy, delta x, delta y. Okay, so this x minus c, that is delta x or dx, same name for that. By the way, some books have a different idea of what dx is. They say it's only when you let delta x go to 0 that it's exactly equal to dx, but we're not going to worry about that so much. What about delta y and dy? Well, the exact change in f of x from here to there, let's put a point there. Try this. So this value and this value, that vertical distance, is that the exact change in y following the function, or is that the approximate change? That's the exact change. So that vertical distance is delta y. And then our new point, our point on the tangent line, is up there. So over there to down here, the original y value, this was f of c, this is L of x, and this is f of x there. That is our approximate y value, our approximate change in y. So that's what's going on here. We're anchoring here, moving, in this case, forward, but it doesn't have to be forward. The original function is changing this much, and we're trying to approximate how much it's changing there. So in this case, what would you say is bigger, delta y or dy? Pretty clearly dy, but that's not always true. If the function was doing something else, maybe dy would be smaller than delta y. Also, these are positive, but that doesn't have to be true. If the function was behaving differently, then some or all of them could be negative. So let's write that here. So here in this example, dy is bigger than delta y, and dy, delta y, dx, and delta x are all positive. But if the function behaved differently, or we did something different with x and c, that wouldn't have to be true. The dy versus delta y could change, and the positive versus negative could change. And it wouldn't just be rare cases. It's just basically equally likely, based on what the function is doing and where you are, that one would be bigger than the other. So here's a good way to test yourself on the understanding here. Try drawing scenarios where dy is smaller than delta y, or where dy is bigger than delta y, but delta y and dy are both negative, or one is positive, one is negative, or dx or delta x is negative. And if you're curious about that, send me an email with your sketches.